So I think today we'll do the first column, and next time we'll do the second. And the first part, in better times, this dynamic logic of programming, in better times, you would have heard that at like in any advanced course in software engineering. So that's kind of familiar, and there is about 50 years of literature about that. So the reason to listen to me is to get 50 years summarized in 20 slides. And then this other stuff contains this parametric post-training is based on Kolmogorov structure function, which is beyond you. But again, reason to listen to me is that I'll try to explain to you what it is, even if you don't have the math background. And then we will make these logical constructions for persistent attacks and protocols for something that is impossible outside of the realm of AI. That is thought to be impossible in security, but now in this new situation, it is demonstrably not impossible. And then in the end, we're going to even tread into some other people's territory and try to see what kind of possible evolutionary principle might there be behind the existence of artificial intelligence. Because if artificial intelligence is possible, then there might then the question of how does the realm of artificial evolve? It evolves, and things are happening that we didn't design, which emerge not by intelligent design but by evolution. So that question emerges. But that's going to come next Friday after I kill my phone. So how do I dynamic logic? Did anyone encounter that? Do we know what's dynamic logic? We used to study it. Software specifications. Dynamic logic is I skipped a slide. I skipped several slides. How do I go back? I don't know what's happening with my. I have to not touch anything but space. Dynamic logic is the logic of program comments, believe it or not. And it's very formal. So we need it here because the idea of our AI safety is something like if a bot learns from a prompt some security constraints, such as that it is speaking with a child, then its response should be adequate to that context. And the precondition which determines the response and the post condition which it needs to satisfy in order to be safe, if you think of the language model as a program, then this precondition and post condition can be thought of as program comments. And that is what we'll be doing. So maybe you know this dynamic logic not as dynamic logic, but as assume guarantee formats of software specifications. That's a standard, various among you asked me whether to study this or not, and if you do I recommend that you study this or not, and if you followed my previous recommendations on first 2 or 3 pages of various of those recommendations, you would have found summaries of the assumed guarantee format. So by asking that you just show me that whatever I recommend, you don't follow it. But this is the fairly basic logical format that we encounter in software specifications. And here's a general example that security specifications are in that format. So because the general format of an authentication protocol, protocol requirement is that we want that if Alice initiates a channel with Bob, and then they run an authentication protocol, then the post condition, if the authentication is correct, is that the responder should really have to be Bob, that no one else can authenticate Bob except Bob. So this is the format which is familiar. These preconditions tell us what is assumed about the software system that we are building, and the post condition specifies what is required that it delivers. So, and you know, at the lowest level, these are the program comments in high level specification. So here's the simplest one for factorial function. The precondition would be compute factorial, and then you, in principle, can say that in your own language, whichever language you like, and the post condition should be that the result is correct factorial. Tony Hoare in 1972 and Bob Floyd at 1969, I think, formalized. They built the formal logic to assure that software specifications are correctly translated into code. So here is what an implementation of factorial, in this case in Python, would look like together with the comments, and you would write a comment which would tell you what are the variables which you specify, and then you would, in the comment, specify something from which you could extract the invariant of your while loop. So do I need to talk about this, or is when you read this, you know exactly what's happening here, and what is the purpose of these comments? These comments help you understand what the program is doing if you don't speak the language. If you don't speak the programming language, if you just speak, in this case, English, or if you just speak logic. And so what Bob Floyd and Tony Hoare did is they introduced the discipline. You know, there was always that battle of programmers do not write enough comments. So let's make a discipline of these comments. And they said every command should be preceded by a precondition and a postcondition. So here's an assignment command, and notice that that things are kind of backwards. You know, you can't, in precondition, you don't know X may or may not be initialized, and you can't say anything about X, but if N is even and you assign N to X, then you know after post condition is that X will become even, whatever it might have been later. So that's the preconditions and post conditions. And here is our factorial little script with a precondition and the post condition. So the same two comments, just slightly more disciplined in a more formal way, and we're using the programming language expressions, in this case Boolean, as conditions, as this meta language to speak about programming. But then when you, and of course, the purpose was to make sure that we can say what we want from the program, develop the program, and if we have correctly annotated our program with the corresponding comments, with the corresponding program annotations, it's a different name for comments, then it must be correct. When you try to do that for loops, then it turns out that here, for instance, if we just try to to look at this, you will only cover the first run through the loop, and after that, your precondition and postcondition will not be satisfied, so that we need something called invariant. Do you know what are loop invariants? Do you remember that? I mean, if they, yes, someone? If they taught you the loops, they must have taught you that you have to see what the invariant of your loop is, because it needs to be satisfied and through all runs of the loop. And then the logic begins, for instance, when this discipline of finding. So do you see the invariant is something that is valid when I enter the loop? Then the value of result changes. I multiply it with I. The value of I changes. And then again, for these two different values, the invariant is still satisfied. Do we see that? All right. And here's the rule then, dynamic logic rule or Hoare logic rule for loop. This is the rule which works. So if precondition implies the invariant, you will be running through the loop as long as the invariant and the entry test of the loop is satisfied. When the entry test and invariant still is not satisfied, if they imply the post condition, then you can say that your while loop satisfies the requirement that the precondition is satisfied at the beginning and the post condition in the end. But this has been a long sentence, but it's simple. Is it clear to everyone? Because we kind of. So if I'm just reading the rule, and the rule says that I'm justified in that the meaning of my while loop satisfied the specified the specified assumption, the assumed precondition will guarantee that the required post condition will be guaranteed if everything that's written above the double line is satisfied, namely that the precondition implies the invariant, that the invariant, as long as the conjunction of invariant and test is satisfied, I need to keep going through the loop. When test stops being true, so that invariant and test are not satisfied, but invariant and not test are satisfied, if that implies the post condition, then I'm good. So the upper block defines the meaning in dynamic logic, the precondition, post condition, assume guarantee format of the while loop. And then we write it, then in order to work with this, then, just like all logical derivations, your propositions and predicates need to be in line. So we breach, usually you have your comments in separate line or separated, but in dynamic logic, we need to make the soup of everything which contains these predicates, in this case enclosed in square brackets. When you see a square bracket, inside is the predicate. Predicate can be precondition or postcondition. And program expressions are in curly brackets. And we write all of that together. So what is written here is exactly the same as what was, I shouldn't be doing this. What was written here. This and this is the same. It's just a matter of writing, but we want to go from programs, which are programmable, to language models, which are learnable. And the same logic will apply. That's why we're learning belated software engineering. So, this soup, which I mentioned, is the soup, in logic. If you had logic course, everything is a predicate or a proposition. Here, or on the other hand, if you are programming, everything is a program expression. And here you have both kinds of things, and that is what your commented code contains. Your comments are predicates, which, if they're relevant, are saying something about the program variables, but you're perfectly welcome to write a love letter to someone in a program comment, and not that it has rarely been done. Have software engineers among us ever done that? No, your generation doesn't write love letters. Do you write love letters? It's a major shortcoming for program code if there are no comments with personal messages. But yeah, maybe we have lost that, but we have not lost the efficiency of dynamic logic, which will now bring us in the realm of AI. So no, but I first need to torture you a little bit more to prove that this is the proper logic where you can, calculate things and you can run programs without running them. So this is just the summary of pretty much everything I've said. The intended meaning of the assertion. Okay, I wrote this down, and I'm assuming that you are reading it, but maybe did you all read this? So there are three kinds of things. I said it's a soup of program expressions on one hand and predicates on the other hand. Program expressions, we write them A, B, F, and G, little letters. Predicates, we write big letters. And then we make triples of these things. They're called 4 triples. They are the assertions. And I write them in this form. Predicates are in square brackets, P and Q. And in between them is the little program expression, little a. And a triple like this is what Tony Hoare called an assertion. And many people call it simply Hoare expressions. And then, and the meaning of a triple like that is P is a precondition, Q is a postcondition. The precondition is what is assumed, the postcondition is what is guaranteed, and in between them is the program or program expression, which changes the program variables in P so that when they come out, they become program variables in Q and they satisfy Q. So the trivial program, these programming languages where you enclose a component in curly brackets don't have explicit skip, but programming languages before that. So program which doesn't do anything, just outputs its input is called skip. And sequential composition, with respect to sequential composition, dynamic logic behaves like this. If you have a precondition P and a postcondition Q of program A, and a Q is a precondition of program B, and it gives postcondition R, then the sequential composition of A and B will, if we assume P, guarantee R. All of this is fairly obvious. And then we introduce the entailment between predicates or properties. So it simply means that P implies Q, or as a property, it's contained. And then with respect to this property, we have, if we have something that is stronger than P and something that is weaker than Q, so if we have P prime, which is stronger than P, and Q prime, which is weaker than Q, and the program A, if we assume P guarantees Q, then if we assume something weaker, such as P prime, it will guarantee something weaker, which is something stronger. If we assume more than necessary, we can certainly afford to get less than necessary. All right? So it's the next rule. And the skip also is equivalent with the entailment. And then the logical, the propositional connectives act as you would expect. Well, maybe not what it says is that the assertions that the four triples are covariant, they go forward, they strengthen things on the right and they weaken things on the left. And I wrote this out. Okay, so if we assume true, I mean, that is the empty assumption, true is always true. And if we guarantee that the true predicate will be satisfied on the output, we are guaranteeing that output exists. So this means that that program A always runs and terminates. Have you taken? So do you all know that it is not decidable whether a program terminates? Have you taken basic concepts? Right. So what this tells us then that we're looking at the logic where the statements, which is too expressive for its statements to be decidable. You can impose, you can require that your program terminates. Well, we know that there is no general algorithm to decide whether programs terminate. But if you write a program where you input X and then add 1 to it and output X plus 1, you're pretty sure that that program terminates. So you can sometimes make sure that the program terminates, and that justifies that we have this logic which can characterize, for instance, termination, which means that in general, it cannot always be decidable. And on the other hand, we can also require that the program always runs and never stops. Diverge, always diverges. That's the second. But the purpose of this slide is just to tell you it's a very expressive logic. It's more expressive than probably than all other logic that you have seen. I mean, and here so now I'm going to summarize the basic rules because we will be, well, not in this lecture, but once you start applying what I will develop for language models, all of this will be needed. So I'm just summarizing again the assignment, this time not restricted to Python, but for any assignment expression, every programming, well, not every functional, don't necessarily have to have assignments, but every programming language which has assignments, this is the semantics of assignment command. If E has a property, if the expression E has a property P, and I assign that expression to X, then X must have the property P. And here is the definition of the dynamic logic clause for branching. So branching, if precondition, if P is guaranteed, if P is assumed, and you run if P, then A else B, then Q is guaranteed if and only if after A, assuming P and T, we will get Q, and after B, assuming P and not T, we will get Q. Again, I'm translating it to English, but I'm probably boring you because this is easier to read in the way it's written than the way I translate it. And here's the one which we have seen, so maybe I should hurry. Here it actually becomes official dynamic logic, and this is the game that will be playing the rest of this. So we can, since programs, there are these at the bottom, at the end of the day, there are these bit strings. So they are well ordered. You can always you can always reduce your programs to bit strings, and you can say this program is below that program. The smallest program is a string of zeros. The biggest program is a string of ones, and you can kill your CPU if you take the biggest program. Which means that we can take that we can find the smallest program. No, that's what I'm going to come later. Predicates are well ordered as well, and we have conjunctions and disjunctions. I ran ahead of myself. So we define, so these there are two modalities. They are post A and pre A. There are these modalities. So this strongest precondition is read P post A is the conjunction of all post conditions of P and then running A. So you basically, the strongest post condition is all things taken together which hold after I run A after the assumption P. I don't know how to avoid saying after twice on this. And the weakest precondition is the weakest, well, is the disjunction of all preconditions that need to be assumed in order to guarantee that that Q will be valid after I run A. So it is the disjunction of all P's such that PAQ holds. I'm having trouble translating this in English, but I'm hoping that you're not having trouble reading. Is this clear? All right. And this is just saying that there are precondition and weakest precondition and strongest post condition. So we certainly know that P post A entails P post A, and then by definition we know. So we have defined P post A to be satisfied. P post A entails Q if and only if precondition P after A implies that Q will be satisfied. So by definition, this first equivalence, if after P we run A, we will get P post A, and then by the definition of pre, instead of running, we can say that P entails that A pre P post A. And similarly for the post, so this is basically telling you, I'll just finish the sentence. This is basically what's telling you that pre post A and A pre P, no, A post P are the weakest precondition and the strongest post condition. Question.
Could you like point at them while translating? I'm getting lost.
I'm just reading left to right. So the first one, I mean, I might have trouble getting into the screen and pointing. I'm not on the whiteboard. P post A entails P post A is the first. Okay. Now, if you look at just the way we write them is telling you what you need to know to perform this calculation. Observe that in all these formats, we're writing the same triple in the same order, PAQ, right? We know easily from the beginning, we have been using what the thing in the middle means, right? The P, precondition P, after A entails Q. So assuming P and running A guarantees Q. That's what the expression in the middle says from the beginning. That is the basic assertion. Yeah. That's what we started from.
This one?
Yes. And these other two are just translating that expression into entailments. And they are adding to my language of predicates two modalities, post A and pre-A. So what this is saying that in my dynamic logic, so this is the dynamic modality. So in dynamic logic, I'm able to say that if I assume predicate P, a precondition, run a program A, then it guarantees the post condition Q. Now, dynamic logic allows me to express this in logic alone, in predicates alone. And that is on the left and on the right. So I have two modalities which say that if you give me a program A and a predicate P, then there is a predicate obtained by applying modality post A on P, and that is on the left. So P post A is a predicate. Okay? And it entails Q. It will certainly be inside Q. Why? Well, there I calculate strongest post condition. How do I get it? Well, I take the conjunction, the end of all the possible post conditions which are guaranteed, which arise after running A in the environment which satisfies B. So I fully understand that it may not come across immediately because, you know, it is a significant conceptual step for which someone got Turing Award to go from assertions, which are the formats that you know, which are just assertions, are just little programs with comments. There's nothing that you haven't seen. P is a comment in the program which says, here the predicate P is satisfied. Then there is instruction A, and then there's another comment which says, after A, this is satisfied. That's all there is. And that's what they started writing. And then someone said, I actually need logic where I can reason like this without the program, just in logic alone. And that is what they, when Tony Hoare then invented, well, no, Tony Hoare was working with the triple, with assertion. Vaughan Pratt, yet another of my bosses, translated it into dynamic modality. So now we can calculate with these dynamic modalities outside of the program. And we have this, you know, we have this predicate. It's a complicated expression, but we can write it in a simple way. And then software engineers, you know, this was happening since the 80s. Then software engineers were able to collect specification requirements from different customers and to conjoin them into theory and to give them to developers to develop the code which will satisfy all these customer requirements. And it's actually still happening. That's how it works. Our job is to lift that from the realm of programmers satisfying preconditions and post conditions to the realm of how can we convince neural networks to produce language models which will satisfy preconditions and post conditions the way we want. That's our job here. And I'm torturing you with software engineering. Well, I'm torturing you with software engineering because you should have been tortured with this at the second year, and you should have walked in this class knowing. Oh, I'm only torturing you because they let you go without it. But I'm providing this because we need it in order to be able to torture not only developers but also neural networks. That's our mission. Amanda raised her hand.
About the P post A. A is in Q, and then the P times A times Q, that's equivalent to the A post Q, A pre Q.
Yeah, except that I don't know where you get the times. I mean, the triple we can read it either pre-P run A post Q or assume P run A guarantee Q or something
Oh,
like that.
okay.
And these X's are you're reading the modalities and
Yeah.
signs. Yeah. I think they are read. I mean, it's not like there's, you know, anyone will arrest you if you read it in your own way. But I think they read P post A and A pre Q.
Okay. Thank you.
All right.
So it matters what direction is.
Oh, absolutely, absolutely. One is on one side, the other is on the other side. So they're different things. They're different operations, but they have this symmetry, and they're written by similar symbols because the symbols satisfy the same symbol.
Yeah, and the reverse thing, assuming that you have an output and you have a program, you can, the weakest precondition, that you can make assumptions about what the precondition.
Talks about. So then when it, so the top and the bottom are equivalent?
No, I'm sure, yeah, they're different things. They're going in different order.
I think what
No, this is where my write notes. I mean, staring at this will not show you what it should be. Take a, look at this slide, take a pencil and convince yourself that you believe. Because at each of these equivalences follow from the definition on 2 slides ago. I'm not claiming this here. This is the thing on the in the first line on the right and in the second line on the left look crazy. The 2 lines are the proofs because the thing on the first right on the left is obvious.
Yeah.
The thing on the second line on the right is obvious, and the crazy things are obtained from obvious things in 2 steps.
Okay, that makes sense. Thank you.
Easy peasy, everything. Let's go on. Ha! So we know that computations can be programmed. I'm just now repeating stuff from previous 2 lectures, and similarly, I'll get to that, but I'm summarizing what I have now said in pictures. So computations can be programmed, and I'm reminding you about that notation. So there's, in the first line, we have a computation F. Someone asks you to write a function. In the second line, we have the interpreter in some programming language. We use Python. So imagine that U is Python interpreter. And so for any computable function that I ask you to program, you can write a program A such that if you interpret it in the interpreter U, you get that same function. The equality is satisfied. And the blue arrow is the process of programming, which I clumsily tried to denote by using chalk for both word programmed and for the arrow, but that's invisible. But that's what I meant to achieve. All right. So blue arrows, these blue arrows were from my first lecture, I think. It denoted program. And if you remember, then I write the red arrow on the other side, which denotes learning. And I'm connecting the 2 because programming is one way to get programs from functions. And learning is another way to get programs. And we want to lift the discipline of securing and making more dependable programs to achieving the same properties in models that we learn, which are programs in some very special and very convenient and very important programming language of neural networks. So we remember that computations can be programmed, and now we have learned that they can be programmed to satisfy the assumed guarantee requirements. So not only can we write can we find the program A such that when I interpret A by interpreter U, I will get the same input-output relations like the function F, which was my programming task, but I can also assure that that for precondition P, that if I assume P, Q will be satisfied, that some properties are satisfied. Observe that this cannot be guaranteed by, for instance, termination. Again, we can't. So dynamic logic can express much more than just mapping functions to programs. They express more than just input-output relations. This first diagram said, given an input-output relation of a function, I can program. But now I know that also, if some assumptions, if all of my inputs are even, my program will always terminate, something like that. So, another reminder, programming versus learning. Do you remember these pictures? I ranted a lot about them in the 2.5-hour lecture last time about this other one. Do I need to repeat what these pictures mean? Do I? No, I don't. Everyone understands what they mean. Okay, so there is this. We are getting program from the given program from a given function specification or requirement, and we have the supervisor, if you want to call it F, or teacher, what Alan Turing called it, which is again a computable function, and we have a loss function, and we have a neural network architecture U now, and by learning process, by gradient descent or whatever you have it, we can obtain the model of our supervisor. We can learn the model as a program. And now we want to enrich that process by some specification requirements so that we can ask, as on the first slide, which I said, if you're talking to a child, you must not curse over them. You must not produce any adult content. We want to be able to require that from a chatbot built on top of a language. That's why we're introducing these assume guarantee logic. Okay, so now to summarize where we are, program logic supports reasoning about internal states and operational requirements in computation. So we can specify termination requirements, we can specify information flow requirements, we can make input confidential, we can require integrity of computation, we can do all kinds of stuff using program logic. We can do much more than just specify input-output relationships. Now, the corresponding thing is education of neural networks. Education is what comes after training. We first train babies to. I know how it's all said in Dutch. I don't even know how it's said in English. Yes.
All right, so I have a question. Is this like the education part is kind of similar to like the fine tuning, like kind of
Exactly. That is you're just getting where I'm going. not similar, it is fine-tuned. That's precisely where we're going, but we need to, you know, peel it open and to get into it and see what exactly needs to be done. And there it gets, that's our job. But that's exactly what it is. You know, we first train them, and we first pre-train them, if you like, and then we post-train them. But there are the language of post-training and fine-tuning has already been polluted by all special cases. So, you know, the overarching word, which is covering everything that comes after pre-training, is the education. So it supports reasoning about internal states and operational requirements, exactly the same like program logic. And now what you are pushing on it is that not only can it make syntactically well-formed sentences, and not only can it make sequences of sentences which are semantically coherent, but you can impose on it text structure, style, format. You need to write in style of William Shakespeare. You need to write a legal document. Then various basic conversational protocols are also post-trained that, you know, if you try to talk to vanilla OpenAI GPT, and you ask it a question, it will give you continuation of your question. You need to post-train it so that it recognizes that after it has interpreted the question, it needs to produce an answer and not a continuation. And how is it doing? It is still producing continuations, but it is post-trained on the restriction of the corpus, where after every question doesn't come a continuation of that question, but the answer. And that kind of education brings us in the realm of safety and security. And if you think about it, it's an appropriate word because, you know, that's actually what parents and society does with children. You know, we train each other to speak and to go through life and to make sentences, but we need to educate each other to not become psychopaths, sociopaths, criminals, and so on, to assure a safe and secure society. That's a matter of education. Let's go there. So post-training, as Ira told us, supports reasoning about internal states and operational requirements. And that is what we need to figure out. So while computation, of course, can be programmed, programs can be learned. We have gone through this already. And now we need to expand it. They can be learned through post-training. And in such a way that the assumed guarantee requirements hold after post-training. So this fully brings us into the realm. Henceforth, we will only be asking questions about fine-tuning. So we're assuming that all the world of P from GPT is settled, and in order to achieve security, we need to structure the discipline of post-training and fine-tuning. So what are the so post-training? The same thing. I don't know whether I need to read, but the same thing is after we have trained our language model to generate language, we need to post-train it to answer questions, to be polite, to not curse, and so on and so forth. And what are the formats? Well, the simplest one, we went, I think, through the forms of fine-tuning in the last presentations. The simplest one is just adding more corpus. It's continued pre-training. And then there is supervised fine tuning where you leave the language model which you have built, and you add additional components. You train it to protocols in such a way that the required preconditions, that the given preconditions are implying the required postconditions. So all the examples of assumed guarantee requirements, for instance, authentication, apply here. So we can impose on top of a language model. We can impose just abstractly. We can train it to run some authentication protocol, and there are already chatbots which are authenticating you in various ways. And yeah, and the existing formats of protocol learning, I'm just reminding you, within the same picture would be to run in parallel several learning processes, but that's not where we're going. The important part is that the most general form of post-training is parameter fine-tuning. So in addition to the prompts, which are of type X, we are also separating the parameters in the corpus. So you partition the corpus into the part on which the model will be pre-trained and the part on which the model will be post-trained. And this partition can go to any number of rounds. And these rounds are parameterized by this parameter theta. So this is what we would like to have. And now the question is whether that is possible, and whether that format of post-training of arbitrary language models is available. So the question is, does every training corpus allow this partition into post-training type of parameters and pre-training type of prompts for any assumed guarantee requirements? So for any notion of safety and any notion of security. That's the question that we need to address in order to make sure that AI security even exists. So can machine learning always continue as machine education? It's not an easy, if you think about people, it's not an easy question. I mean, the human society exists, the human society kind of branches over this question. Some of us are more interested in continuing to refine the capabilities, the language capabilities which we acquire. So, and these are the questions about pre-training and post-training. Okay, so what would this parametric post-training be? So can every model A be parameterized, and every model be learned up to this parameter type theta? So when you start pre-training, when you have a corpus and you want to pre-train your model, can you always recognize the part of the model or partition that model into a parametric way so that you can leave parameters for post-training? That's the question of this discipline. And towards the answer, first of all, let us remember that the idea of Turing complete languages or universality of interpreters means that for every computable function, there's a program. And do you all, so now I could, there's a big part of programming discipline which talks about partial evaluators. Does everyone know what's a partial evaluator? Have you used partial evaluators? I mean, so yeah, I hear you. Partial, if your program requires the idea is deadly simple, and it's the most important part of the invention of programming by Gödel and Alan Turing. But the simplicity of the idea is deceitful. The idea is simple. If you have a program which requires 3 pieces of input, and one of these 3 pieces of input is available and the other 2 are not, you will get them tomorrow, then you can partially evaluate your program. How do you partially evaluate it? Well, I mean, these input variables, they occur somewhere in the program code. And if you have values for the input variable which is available, then you can plug them in. So everyone is looking at their screens. Have I bored you enough to do you want a break? I'm kind of worrying that you stopped following me, and we are getting, it's kind of increasingly, we're getting to more important parts. I may be over explaining these parts, and I may have bored you in the wrong way. Should I just hurry, or should I give you a break? Vote, hurry. Vote, a break. No one wants a. Yeah, some people want a break. Let's have a break.